Who has a greater speed?
He does.
Yeah, even without any other information, you pretty much have that. But he goes 400 meters in 40 seconds, so he's going 10 meters per second, which is roughly 22 miles an hour. Whereas I've gone maybe 100 meters in 40 seconds, so I'm going, yeah, that might be realistic. 2.5 meters per second. It was a higher magnitude of average velocity.
He does.
Why?
Not sure.
But you took a chance. You know, if in doubt, it's a 50-50 chance there. Average velocity. What is Usain Bolt's average velocity?
What? 10 meters per second.
No.
0 meters per second?
Why?
Because he started and finished in the same place.
Yeah. It took him 40 seconds to go nowhere. Whereas after 40 seconds, I'm somewhere. I'm somewhere else. I have a greater displacement than he does in the same amount of time. Therefore, I have a higher magnitude of average velocity. I am faster than Usain Bolt, as long as you look at it that way.
Kind of like a ninja, like you want to see me do it again.
Say it again?
Like a ninja when you say, oh, you want to see me do that again.
Yes. Or Muhammad Ali.
Mm.
Questions to hear? Okay. Now the one that can mess with people's heads. Mathematically, I wrote it over here, it's the change in change in position over change in time, or displacement over change in time. Now, oftentimes, instead of a delta t, I'm just going to write t, and I can't remember if I did this last time or not. Delta t, because it's a change, would be the final time minus the initial time. Initial time is just, you know, whatever I choose. And typically, if I choose my initial time to be 0, so the problem starts at time is equal to 0. So if I set that equal to 0, then this just becomes final time minus 0, which is just the final time. In other words, it's just time. You know, how much time has passed since you started. So oftentimes, I'll sometimes write delta t, sometimes I'll write t. So just be aware of that. If I look at the change in velocity over the change in time, this is acceleration. Anyone want to take a shot at what the symbol is?
Delta V.
The change in velocity would be delta v. Yeah, it doesn't follow that pattern.
And that's not the same as acceleration? The change in velocity?
No, because there's a time element involved with acceleration. If I go from 0 to 60 in 5 seconds or 0 to 60 in a minute, there's a very different acceleration there. Yeah, they got real clever with this one too. More than just an A though.
With the vector symbol.
Yeah, all right. So that's the symbol for acceleration. I'll go ahead and spoil it. The scalar word. The scalar analog is acceleration.
You said it's acceleration again?
Yep, it is just the A without the vector symbol. It is unfortunate that it's the same word. So if you're asked a problem, how do you know which one?
It has a line or not.
Say it again?
It has a line or not, vector symbol.
Yeah, so what I try to do is when I write acceleration is put either the A with the vector A or the scalar A symbol after it. But oftentimes it is context. And yeah, if in doubt, try to do the vector one, but if there's not enough information, it's probably the scalar one. I know, it's not a particularly satisfying way of telling the difference. Take physics for a few years and then it becomes obvious. But on tests and quizzes, I've tried it with the A with the vector symbol or A without. If in doubt, ask.
What was that A word?
Pardon? What is this word?
Yes.
Acceleration.
Oh,
It's the same word.
okay, thank you.
Yeah. At least there's a difference between speed and velocity and distance and displacement, but unfortunately not with this. There are, of course, two kinds. Average and instantaneous. I'll just shortcut that. And the default is instantaneous. So if I ask what's the acceleration, I'm asking about the instantaneous. Now it turns out we will deal with a lot of problems where acceleration is constant, thus the cake formulas. And if acceleration is constant, then the average and the instantaneous are the same. However, not for the plus minus zero. So this is the rate of change of velocity. Technically, time rate of change of velocity. So as a driver, there are three things that a physicist would call an accelerator. Because in order for there to be acceleration, there needs to be a change in velocity. What are the three accelerators that you have access to as a driver?
The gas pedal, the brakes, and the steering wheel,
Yes. How does the steering wheel cause acceleration?
because you're still moving in a direction.
Okay, more specifically, it changes the direction.
Okay.
Now, for a lot of chapter 2 and 3, we are primarily going to deal with acceleration because of change in speed. Chapter 6, we get into more specifics of acceleration because of change in direction. All right, so if my velocity starts out at -10, so let's make this my velocity, and time in seconds. So time 1, 0, 1, 2, 3. And if my acceleration is 5 meters per second squared, what I'm claiming is that my velocity changes by 5 meters per second every second. So after 1 second, I'm going -5, then I'm going 0, then 5, 10, 15, 20, 25 meters per second. So this would match this idea of a constant acceleration of 5 meters per second squared. So my acceleration is positive. So when I'm first starting out though, am I speeding up or slowing down?
Slow down to the second.
Negative, so aren't you going in the opposite direction?
I'm going in the negative direction, true. What's happening here?
You reached the starting point?
No, I don't. The starting point can't be figured out from what I've given you here.
Is it the
You're slowing
constant?
down. You're slowing down because you're approaching 0 mile.
Yeah. 0, I stopped briefly. What's happening in the overall context at this point?
Nothing.
Basically, you was going in reverse and then you stopped, and now you're going forward.
Yeah, so this is the point where I turn around. Now my acceleration is still positive 5 throughout the whole thing. All right, so at the first part, I'm slowing down because I'm getting closer to 0. Then after that, what's happening here? Yeah. And let's get rid of some of this stuff. We'll see what gets erased. Oh, okay, that's what it was. All right, so I've got a positive acceleration here, but it means I'm slowing down at one point and I'm speeding up at another point. So looking at the sign of my acceleration does not give me enough information of what I'm speeding up or slowing down. So let's now do, I'm at, say, we'll do time in seconds, and start at 0, and velocity in meters per second. So we'll start at 30, and this time my acceleration will be a constant -5 meters per second squared, which means that every second it changes by -5 meters per second. So after 1 second, what's my velocity?
What were you going by again? -5?
-5.
Is it 25?
Yeah. Keep going.
20, 15, 10, 5, 0, -5, -10, -15.
It looks like the classes of like the Jew spokesperson, so congratulations. Other people could have joined in. All right. So in this first part right here, speeding up or slowing down.
Slow down.
And in this part,
Speeding up.
speeding up, speeding up backwards. Or maybe I was slowing down backwards and speeding up in the right direction. So, but I'm speeding up either way. So is there some generalization about when acceleration is speeding up and when is it slowing down?
No, because if you move and you're speeding up by default, right?
So say that one again?
If you're moving, you're speeding up by default. There's no,
Not necessarily. We're moving here, but slowing down.
I can't explain.
Wouldn't the generalization be based off of whether or not it's positive or negative?
How so? Because here it's positive and it's slowing down and speeding up. There it's negative and it's slowing down and speeding up.
Always slow down before 0 and speed up after 0.
What do you mean before 0 or after 0?
Well, because it starts at, the closer you get to 0 from your original point, in both the problems you were slowing down until you reach 0,
Okay.
then you started speeding up.
That is true. The closer you get to 0, as you approach 0, you are slowing down.
What I'm trying to say is, the closer you get to 0, you slow down, but any direction other than that, you're speeding up.
So if you're not slowing down, you're speeding up?
I can't explain it, yes.
There is another choice of your velocity is not changing at all, acceleration of 0. But, okay. We can come up with, I think, something slightly more generalized than that. Notice I'm slowing down here. What's my velocity? Positive, negative, or 0?
Negative.
And my acceleration?
Positive.
And I'm slowing down. Here, my velocity is
Positive.
Positive.
my acceleration,
Positive.
speeding up. Over here, velocity,
Negative.
Positive.
Or positive.
my acceleration,
Negative.
slowing down, speeding up,
Positive.
Negative.
they're both negative. So if my velocity and acceleration are the same sign, I'm speeding up. If they're opposite signs, I'm slowing down. Now why? This will involve some stuff that shows up in chapter 4, but a little sneak preview. What I consider the most important equation in all of physics, Newton's second law. The total force is equal to the mass of what the forces are acting on times the acceleration of that object. The force and acceleration are the only two vectors in this, they have to be the same sign. They have to be in the same direction. The total force and acceleration are in the same direction. So if I'm walking in this way, whether this is positive or negative, it doesn't matter. If I'm walking this way and someone pushes me in the direction I'm already moving in, well, I speed up or slow down.
Speed up.
If I'm walking in this direction, whether it's positive or negative, and someone pushes me opposite the direction I'm moving,
Slow down.
so when the force is opposite the velocity, in other words, when the acceleration and velocity are opposite signs, I slow down. If the force is in the same direction of movement, acceleration and velocity of the same sign, I speed up. Questions to hear? Mark?
But you would stop if it was an equal and opposite force hitting you in the opposite, direction. Or would that still slow you down?
Give me some more detail here, what you're
Okay,
asking.
if you're walking in one direction.
Right.
We'll say positive, and then something that is equal comes in the opposite direction, negative, would you stop completely?
Equal to, all right, so if the force I'm applying to move in that direction is matched by force in this direction of equal magnitude,
Right, yeah.
my velocity would then not change. I would be in equilibrium. If I'm moving, it's called dynamic equilibrium. If
Okay.
I'm not moving, it's static. But if the total force acting on you is zero, acceleration is zero, and therefore change in velocity is zero, in other words, velocity does not change. Which is basically Newton's first law, that an object will keep doing whatever it's doing unless something changes, unless a force is applied to it, a net force. All right. When we take a small little break here, stretch legs, I'm going to write up a test level problem, which will look a whole lot in the similar vein to, I think, the last question on master set two. We want to have master set two right here in front of you. On your desk?
No, it's on my phone.
Oh. Anyone have master set two easily accessible?
Pull it up on my tablet. That's what you want that.
Yep, sure. That's what we got. No, I guess I need to see it first. Yes. Get that thing. Chapter two, yes. The backup, cancel. Want that. Just press up the second one. And it's just scroll to the bottom. All right, that's what I wanted to see. Thank you.